What makes us human? The answer to this question might differ from one person to the next. Is it our evolutionary trajectory? Is it our intelligence? Our self-awareness? Our interpersonal connections? Well, one undisputable certainty is what makes us human at the most microscopic of levels. Because when considering our humanity with this framework, the story of humanity becomes a story of our intimate connection to the universe. And today, I'm going to take you on a trip through space and through time as we uncover the origins of life's fundamental building blocks, the foundational pieces of this puzzle that we call life. So what are these building blocks that I'm talking about? Our bodies are composed of blood and bone and organs working in concert, each of which are an amalgamation of cells, tens of trillions of which are inside of every single human body. These cells metabolize energy, they replicate, they store our genetic makeup, they provide structure to the body. But if we dive even deeper than that, we see that all of these cells are composed of atoms. Oxygen, hydrogen, carbon, iron, all of these elements that comprise the periodic table are atoms of different sizes and are the building blocks of everything around us. We have about 1 billion times more atoms in our body than the number of grains of sand on the planet Earth. In fact, there are even more atoms in a single human body than the number of stars in the observable universe. But despite their ubiquity in us and in the world around us, astronomers are still trying to uncover the cosmic origin of many of the atoms on the periodic table. So where does our origin story start? It starts at the ultimate beginning, the beginning of matter and energy and space and of time. Although astronomers can't see this far back even with the most powerful telescopes imaginable, we can infer what was happening in our nascent universe by looking at stars, galaxies, and light from the distant past. The Big Bang, the beginning of our universe, was measured to have occurred a little over 14 billion years ago. And within 1 second after the Big Bang, the protons and neutrons that make up the nuclei of atoms formed. But to hold on to electrons and become bona fide atoms, these protons and neutrons had to wait. They had to wait for the universe to expand and cool from its hot and dense early state. It took hundreds of thousands of years for this to happen. But at 380,000 years after the Big Bang, these conditions were met and atoms were born. At first, only the lightest atoms were formed. Hydrogen, the lightest element on the periodic table, was by far the most abundant, with some helium and trace amounts of lithium. Why does that matter to us? There are more hydrogen atoms in our bodies than any other type of atom. We're about 60% water by weight, and for each one of those water molecules, we have 2 hydrogen atoms holding on tight to an oxygen atom, giving us the H2O that we know so well. These hydrogen atoms inside of every single water molecule in your body have experienced nearly the entire history of our universe, being synthesized in this soup of primordial particles long in the distant past and connecting us to these nebulous and distant times. But at this early time, most of the atoms on the periodic table still did not exist. What about the oxygen that is a part of every one of those water molecules? What about the carbon that's the building block of organic molecules, or the nitrogen in the air around us? For these elements to form, we have to go a little further into the future, just a little bit, 100 million years. This seems like a long time to wait, but in reality, the universe was still in its infancy at this point, less than 1% of its current age. At this time, vast clouds of primordial gas were pulled together by gravity until they were able to start to collapse under their own self-gravity, becoming denser and more densely packed in the process. Then, something amazing happened. Deep inside of their cores, the gas became so hot and so pressurized that it began to transform. The hydrogen atoms in the cores of these balls of gas started to fuse together, releasing energy and churning out heavier and heavier elements. And this marked the birth of the first stars. Stars create their energy through this process, like I was explaining, called nuclear fusion. And it requires really extreme conditions, but also lets out an immense amount of energy in the process. To give you an idea of just how energy efficient fusion is, if you were to take one water bottle's weight of hydrogen and turn it into helium, it would be enough energy to power the entire United States for almost 2 minutes. Now, a typical star like our sun is fusing the equivalent of 7 billion water bottles worth of hydrogen every single second. The energy released from this fusion process pushes back against the force of gravity that's trying to collapse the star into a smaller and smaller and smaller size, facilitating a sort of cosmic balancing act that can last for billions of years. Stars live their lives in this delicate balance, and in the process churn heavier and heavier elements out of lighter ones. First, they make helium out of hydrogen. Then they make carbon and oxygen out of helium. And then, if the star is big enough, neon, magnesium, silicon, and so on, until finally the core of the star is made of iron. Iron, which has 26 protons in its nucleus compared to hydrogen's 1, is the end of the line for fusion of stars, leading to gravity being the final victor of this tug-of-war game that lasted for eons. With nothing holding it up anymore, these stars will collapse and possibly trigger a supernova explosion. These violent deaths of stars not only enrich the cosmos with all of the atoms that were being created and forged within their cores, but they actually have extreme enough conditions to synthesize things that are even heavier than iron. So take a second to think about this. The oxygen in the water that we drink and in the air that we breathe. The carbon that is the backbone of proteins, carbohydrates, and other complex molecules. The nitrogen that is crucial for building amino acids. The calcium in our bones and the iron in our blood. All of these atoms that are essential for us as humans were forged in the hearts of stars and enriched the cosmos with complex diversity when these stars ended their lives. The atoms in our body likely also did not just live inside of one star. They likely lived inside of multiple stars before ending up where they are today. The atoms in our bodies saw their systems of ancient planets, and perhaps were even a part of alien life forms. Our bodies, at their most fundamental level, are intricately and intimately connected to the universe across vast amounts of time and space. So what is my small part in this creation story? Well, the idea of stars creating their energy through nuclear fusion and churning out heavier and heavier elements in the process has been around for over a century. But just a decade ago, our periodic table was still far from filled. The cosmic origin of many of the elements heavier than iron, such as gold, silver, platinum, and uranium, was still a mystery. We understood pretty well that these elements couldn't be created solely from the lives and deaths of stars. However, there were other objects in the universe, more exotic objects, that were prime suspects for their creation. When a star that is about 8 times or more massive than the sun ends its life in a supernova, it can sometimes leave behind a compact core that's called a neutron star. Neutron stars are incredibly small in cosmic terms, only about 10 miles across, the size of a city like Chicago. But they are packed with more mass than our entire sun. This makes the matter that's inside of neutron stars the densest and most extreme form of matter that we know about in the universe. To give you an idea of just how crazily dense and exotic these objects are, if you were to take a single spoonful of neutron star dirt and weigh it on a scale, that spoonful of neutron star dirt would weigh more than all 8 billion humans on Earth combined. Now, sometimes these neutron stars can find themselves in a binary system where 2 neutron stars are in orbit around one another. Thanks to Albert Einstein, we know that as these objects orbit each other, they distort and create ripples in the fabric of space-time itself. These ripples are called gravitational waves, and they cause the orbit of these neutron stars to shrink and shrink over time as energy is lost to the gravitational waves. The neutron stars out in the universe thus inch closer and closer and closer and closer together, emitting stronger and stronger gravitational waves in the process until they inevitably merge. So I am part of an international scientific collaboration that uses instruments called LIGO to measure these elusive ripples in the fabric of space-time. It took a full century after Einstein predicted the existence of gravitational waves for us to develop the instruments and techniques necessary to observe them. But this all paid off about 10 years ago when the field of astronomy was revolutionized. The first gravitational wave signal we ever were able to observe was in 2015 and was the result of the collision of two black holes, each of these black holes about 30 times as massive as the sun, merging in a galaxy about 1 billion light years away. Now, this discovery led to a whole new understanding of these exotic objects like black holes in our universe, gave us a novel viewpoint of how these black holes form from the lives and deaths of stars, allowed us to test our theories of gravity at the most extreme environments imaginable, and was awarded a Nobel Prize in physics. But when two black holes merge, they don't emit any light or create any new elements in the process. Groundbreaking as this discovery was, the mystery of the cosmic origin of elements persisted. So now we fast forward a couple years to September 14th, 2017, when a new type of gravitational wave signal was observed. Not the collision of two black holes, but a collision of those two dense exotic objects that I was talking about, neutron stars. As these two neutron stars spiraled towards each other, their strong gravity ripped each other apart, casting out dense neutron-rich material into the cosmos. This was predicted to cause something called a kilonova, a massive radioactive cosmic explosion. With the gravitational waves that we measured here on Earth, we were able to identify the approximate part of the sky that this kilonova event would have occurred in. And then telescopes all around the world and up in space scoured this region of the sky to try to find the anticipated kilonova light show. About 10 hours after the gravitational waves were sensed, that search found success. The image that you see here is a picture of a galaxy taken by the Hubble Space Telescope. This galaxy is called NGC 4993. And the orange dot that you see in the upper left-hand part of this image was a new blemish on the galaxy found after this event in 2017. This new blemish, this new bright point of light, was so bright that it could even be seen against the backdrop of the hundreds of billions of other stars in this galaxy. This was the kilonova. This was where these two neutron stars merged. The galaxy itself is about 130 million light years away, which means that this event actually happened long in the distant past when dinosaurs were still walking on the planet Earth. And to this date, this remains the only astronomical event that we've observed in both gravitational waves and in light, allowing us to explore something in the universe with multiple senses, almost like being able to listen to and see the universe for the very first time. So what did this discovery tell us? By studying the light from the kilonova explosion over time, we were able to tell that this system was creating an exorbitant amount of heavy elements, many of these elements whose origins were in question. In fact, from this one event, we estimate that about 100 times the Earth's mass in gold was synthesized. So pretty rich. Now, this was the first direct evidence for many of these heavy elements being created, painting a much clearer picture of how the universe provides the structure and atoms that make up us and the world around us. So when confronted with the vastness of the universe, both in terms of space and of time, many feel overwhelmed and question humanity's importance on this grand scale. But I think there's beauty in the fact that the atoms that make us human, the puzzle pieces of life at their most fundamental level, are intimately connected to the universe across vast amounts of space and time. They've witnessed the entire story of our universe itself. They were there in the first instances of time. They lived in long-dead stars, and they were firsthand experiencing these cataclysmic cosmic explosions. So rather than a feeling of unimportance or insignificance, I hope that with this talk, I've convinced you that we should feel a sense of connection to the cosmos for its role in making us who we are. Thank you.